If we look at this example, this is another theoretical probability. It says represent graphically the probability distribution for the sample space for tossing 3 coins. Well, what do we mean by graphically? Well, the first thing we have to do is find the probability distribution. And if we remember, if we're tossing 3 coins here, no heads, one head, 3 times, you get the picture. So, our probability of 0 heads, again, would be 1/8. 1 head would be 3/8. 2, 3/8. And 3, 1, 2, 3, would be 1/8. We can take this information and we can put it on a graph. It's just kind of look like a bar graph. So, if you see here, we have a probability on our y-axis and the number of heads. So our random variable here on the x-axis, 0, 1, 2, or 3. That's our our 4 choices. 1/8, 2/8, 3/8, 4/8, or 1/2. You could keep going here, but remember, if I take a picture of this, so I have to refer back to it, we can see that all you have to do is make a little bar up to your probabilities. 1/8, 3/8, 3/8, 1/8. Probability on our y-axis, random variable on our x-axis. And that's all you have. That's just another way of displaying the same data in a distribution table here or on a graph. Let's look at another example. Okay, this one is going to be more experimental. It says the Baseball World Series is played by the winner of the National League and the American League. The first team to win 4 games, so it's 4 out of 7. It says the data shown consists of the number of games played in the World Series from 65 through 2005. No World Series in 94, that's when they had a strike. And the number of games played is represented by the variable x. Did they play 4 games in the World Series, 5 games, 6 games, or 7 games? Have to play at least 4 because you have to win 4. Find the probability for each x and construct a probability distribution and draw a graph for the data. Now, this is the number of games played. 8 times they played 4 games in that time period. 7 times they played 5 games, 9 times they played 6 games, and 16 times they played 7 games for a total of 40. It's not our probability. Remember, probability is taking, like we said, 8 games out of our total, and that works out to be about 0.02. And I'm going to traditionally just you write it out a little bit further. So our probability for 4 games played is about 20%. And then do the same thing for the rest of them. 7 out of 40 games works out to be about 0.175. 9 games, again, out of our total. Return the probability that they're going to play, the probability they're going to play 6 games. I'm saying this wrong. This is 4 games. This is 5 games, our probability. This is 6 games. Based on previous data, 9 out of 40 that's happened. 0.225 times. And then 7 games, it's happened 16 out of 40 times. It says construct a probability distribution and draw a graph. Well, this is our probability distribution. The probability of playing 4 games is about 0.2. Probability of playing 5 games, about, well, we say 17.5%. Probability of playing 6 games, about 22.5%. And the probability of playing 7 games is about 40%. Now, it wants us to graph it. And again, this is going to go on our x-axis, our random variable x, the number of games played, and our probability is going to go on the y. So if you look here, probability on our y-axis, number of games on our x-axis, Probability of playing 4 games, about 0.2, a little bit less than 0.2, 0.225, and then 0.4. So just 2 different ways to see the same types of probability, to see the probability distribution. So when doing these types of problems, finding probability distributions, find the probability the exact same way you have. What do you want to have happen over your total? And that's what we did here. And there's basically 2 ways you can do this. We have theoretical, where we know all the outcomes, or we have experimental, where we're given the data. If we have to graph it, probability goes on our y-axis, and our random variable goes on our x-axis.